This video is on linear models and linear regressions. First of all, we want to start with a definition for a linear model. A linear model means that you have an equation of a line that goes through your data. And it summarizes the data in its general pattern. Now, there are lots of other types of patterns. You may have a quadratic model, you may have an exponential model, but we're only looking at the linear models, and so we're only looking at linear types of situations. So we're looking at what we call a linear regression. And that means that is a process of determining the linear relationship between two variables. And it's going to be with a linear equation. Now, just as I said before, because there are other types of equations and other types of data, we're looking at the linear type because you can find other types of models for exponential, quadratics, cubics, whatever. There are regression equations for those types of models, but we're only looking at the linear regression. Now, let's just sketch a linear equation, and let's sketch some data points. This would be a scatter plot. And so if I was going to do a linear model, I would look at a linear model that would model this data, and it's usually going to go through the middle of all those data points. It may hit some of those data points, but it may not hit all of them. It's going to be whichever ones would hit most of the points. And we would want to look at how far away from that line those data points are, whether they are below or above the line or they are on the line. We would want to look at how far away are those data points, and we would study that distance that those are away from the actual model line that we would use. So this is our model line. The line of best fit would be the line that is closest to those data points. So we can come up with lots of different models, but the line of best fit would be the one that would be closest to all of those data points with the least amount of error. There's lots of different ways of doing regressions. There is a mean median method. There is just pick 2 points and find the slope and the Y-intercept with those 2 points. So there's lots of techniques that you can use to find a linear regression, but we're going to use a technique called least squares. This technique of least squares is considered the most practical and the least, or it will give you the best fit overall of any of the techniques that can be used. Now, what the least squares regression is it is the sum of the squares of the vertical distance from the line to the data points. So you see what I have drawn here in our model, our data points in the scatter plot, the vertical distance from our model line to the data points, and that's what we're going to be calculating in our regression. Now we have some formulas that we're going to use to come up with that line y equals mx plus b. That's what we're used to algebraically, but we're going to use some other notation to come up with that model. You might see this notation where we have y with that little hat on it equals b sub 0 plus b sub 1 x. You might also see some other notation in addition to that, depending on different textbooks, different professors. You might see some other notations also used. You might see b sub 0 equals y mean minus b1 x mean. This is also just a different technique of writing, coming up with values for your equation. So let's look at what needs to be done in order to find our values for our equation. There is some formulas that we're going to use. Our formula to find the slope, which in this case would be our b1, is n, and we've seen this summation symbol before, times the x and the y value minus the summation of x times the summation of all the y's divided by the number of data values times the summation of all the x's squared minus the summation of the x and then square it. And so that will be the formula that we will use to find the slope. Now there's a couple of different formulas to use to find that y-intercept. But the easiest formula to use is the summation of y minus whatever answer we get here for m times the summation of x over the number of values. Now, again, there is other formulas that you can use, but this is the most simplest formula in order to use. Now, let's look at a sample problem to use to actually compute our regression equation. So, some sample data. we have some values for x and y. We're going to make a little chart. We have 3, 15, 5, 22, 0, 7, 1, 12, 2, 20, and 6 and 30. And then we're going to need a totals section. So we're going to total up our x's, which is going to be 17. We're going to total up our y's, which is going to be 106. Now we want to continue this chart because we're going to need some other calculations. So we're going to need to make a column for x squared. So 3 squared would be 9. 5 squared would be 25. 0 squared would be 0. 1 squared would be 1. 2 squared would be 4. 6 squared would be 36. And we're going to need that sum. So that would be 75. And for good measure, I don't know that we need that in any of our formulas, but let's go ahead and find y squared, just so we have that calculation in case we need it. So 15 squared would be 225. 22 squared would be 484. 7 squared would be 49. 12 squared would be 144. 20 squared would be 400, and 30 squared would be 900. And that total would be 2,202. And we also need an x times y column. So x times y, 3 times 15 is 45. 5 times 22 is 110. 0 times 7 is 0. 1 times 12 is 12. 2 times 20 is 40. 6 times 30 is 180. And then we need to sum up that column, which gives us 387. So this little chart, we start with the data. This would be data from our scatter plot, or just data given to us, and then we would take that data and create this little chart and this information. And then we're going to use this information in our formulas to come up with our regression line. So using our formulas, we first want to find m, which is also known as b sub 0. So the number of data items, 1, 2, 3, 4, 5, 6, times the sum of x times y, so that's 387, minus the sum of the x's, which was 17, times the sum of the y's, which was 106, all divided by, all I'm doing is placing my values into the formula at this point. So again, using that formula that we have from previously, the number of data items, which is 6, the sum of the x squared column, which is 75, minus the sum of the x column, which is 17, and I'm going to have to square that. So in order to calculate this, now I'm going to go through some of the arithmetic. So I'm going to do 6 times 387. That's going to be 2322 minus, I'm going to do 17 times 106, 1802. I'm going to do 6 times 75. That's going to be 450. And I'm going to do 17 squared. That's going to be 289. So I'm ready to do the subtraction on top and the subtraction on the bottom. And so that gives me 520 over 161, which gives me 3.23 for the slope. All right, the next thing to compute would be the Y-intercept. Whether you call it B or B sub 1, we're plugging in the values. So we're using the sum of Y, which would be 106, minus the slope that we got in this answer, 3.23, times the sum of X, which was 17, all over the number of data values, which was 6. So first we need to do that multiplication. So 106 minus 3.23 times 17 would be 54.91 over 6. And then we do that subtraction and division, and I think we get 8.515. So to build our model equation or our regression equation, we would have Y equals 3.23 times X plus 8.52, rounding that to the hundredths place, same place as the slope. So that is an example running through a regression equation.